the gradient. If you've got a function with two independent variables, your gradient is going to be a two-dimensional vector. But if you've got a function of three variables, then your gradient is going to be a three-dimensional vector, and so on. In fact, if you got a function of four variables, then your gradient is going to be a four-dimensional vector. You can just keep generalizing this on and on. But in my vector, every entry of the gradient vector is a partial derivative of your function with respect to one of the independent variables. So if I want the gradient of a function, you already know how to do this because you already know how to take partial derivatives. We start off and the first entry is the partial derivative with respect to x. So it would be a 2xy. The derivative of natural log x is 1 over x. Okay, and then the second entry is the partial with respect to y. And derivative of sine is cosine. Chain rule says multiply by the z. Okay, and then the derivative, the partial derivative with respect to z would be negative y cosine yz plus 1 over z. Boom. That's the gradient vector. Everybody likes it? Now, the directional derivative of a surface, and I can define a surface by setting the z coordinate equal to a function of the x and y coordinates. That will give me a surface in 3D space. So the directional derivative is going to be some derivative in the direction of the vector v. So we're going to be given a vector v. And that's going to be the slope of the surface in that particular direction. So imagine you're standing on a surface. Imagine you go for a hike out in the hills and there's a lot of topography, right? So the surface around you is changing. Anywhere you stand on the side of a hill, you can rotate yourself and point in a different direction, and the steepness of the surface is going to be different depending on which direction you're facing. If I'm standing on the side of a hill, there's going to be one direction of like steepest ascent. If I point myself towards the top of the hill, there's a direction of steepest descent. There's always going to be a direction where I can just travel and not move up or down in elevation. Actually, probably two directions, right? In front of me and behind me. And then in between those, there's varying degrees of how steep is the hill in that direction. So this is called a directional derivative. The three-dimensional, the multivariable function, three-variable function equivalent of this is to say that I've got the scalar field, so every point in 3D space is associated with a scalar, a number. And if you find yourself at a point in 3D space, well then, if you point in any particular direction in 3D space, how quickly is the scalar field changing in that direction? Is it increasing? Is it decreasing? And how by how much? So this is a directional derivative. And the directional derivative in the direction of v, we're going to write a capital D with a little subscript v to mean the directional derivative in the direction of v. And I want to find the directional derivative of f. This is either going to be plus or minus the norm of the projection of the gradient vector onto the vector v. Why? Because the gradient vector has encoded all of the information about how the function is changing. It's got the partial derivatives for every independent variable in it. Whenever I take that gradient vector and I project it onto the direction I care about, I get only the component of the gradient in that direction. I'm going to take the norm because I don't want to end up with a vector. I just want a scalar that tells me how steep is this, how quickly is my function increasing in this direction. So I want a scalar, so I'm taking the norm. And then this is either going to be positive or negative, depending on whether my function is increasing in that direction or decreasing as I move in that direction. That's what the plus or minus is about. So, if you know your projection formula, the projection of the gradient of f onto v would be, let's talk about that for a second. The projection of the gradient of f onto v is going to be the gradient of f dot v divided by v dot v times v. That's my projection formula. And then if I take the norm of both sides to get the norm of the projection, now this is a scalar already, so I don't really need to take the norm of that, but I do need to take the norm of this vector. And whenever I have v dot v in the denominator, remember that's the same thing as the norm of v squared. So what this norm over here in the numerator, norm of v, is going to cancel out with one of these norm of v's in the denominator. And then what I'm left with is this. And so what I'm circling right now, that's probably what you want to use to actually calculate the directional derivative. Just wanted to show you how you come up with this formula. But if I were going to sit down and calculate a directional derivative, I would find the gradient vector first. I would dot product with the v vector and put v's pointing in the direction I care about, and then divide by the norm of v. Good question. I'm glad you asked. When I take the dot product of gradient of f dot product with v, it's going to be positive if v is kind of in the direction of the gradient, right? And it's going to be negative if v is pointing kind of in the opposite direction of the gradient. Does that make sense? And if they were like at a 90-degree angle with each other, then it would be 0 because they'd be orthogonal to each other. So their dot product would be 0. And so the plus or minus stuff is already represented exactly how we want by this dot product. Yeah, but that's a good question. Yeah, so using that formula that I just circled, it will be positive if the function's increasing in that direction, and it will be negative if the function's decreasing in that direction. So exercise 2 says, find the directional derivative of the following function in the direction of v. So we're just going to use that formula. We just found the gradient of f a moment ago for the same function. I don't remember what we found, but we did do that. So partial with respect to x, and then partial with respect to y. And then lastly, the partial with respect to z. So that's my gradient. And then to get the directional derivative in the direction of v of f, we've got to take the dot product between that gradient and v and divide by the norm of v. So this is going to be 1 divided by norm of v. We'll find that here in a minute. And then let's calculate that dot product. The dot product would be the first term times the first term of v, so it would be like 2 square root of 2 times 2xy plus 1 over x minus 2 square root of 2 times x squared minus z cosine yz running out of room here. Plus 3 times negative y cosine yz plus 1 over z. And then the last part is just finding out what is the norm of v. And the norm of v is 5. Okay, so altogether, this directional derivative is 2 square root 2 over 5 times the first entry in my gradient minus 2 square root 2 over 5 times the second entry in my gradient plus 3 over 5 times that third entry in my gradient. Okay, and so now, if you tell me a point on my surface, like you tell me a point where x is equal to 2 and y is equal to 5 or something like that, well, I could calculate what, oh, sorry, this isn't even a surface. This is a scalar field, right? Because it's a function of 3 variables. So right now my f function in exercise 2 is saying, you give me coordinates x, y, and z, I'll tell you a value f associated with every point in 3D space. And now if you tell me a point in 3-dimensional space, you give me the x, y, and z coordinates, I can calculate for you the directional derivative of the function f in the direction of v, in that vector direction, and tell you how quickly the function is changing in that direction at that point. Does it make sense what we're actually finding here? Yeah. With multivariable functions, there's not just a derivative. It's like, okay, you're taking the derivative, but in what direction? If you're taking the derivative only in the x direction, we're just talking about the partial derivative with respect to x. If you're talking about the derivative only in the y direction, that's the partial derivative with respect to y. But what about the direction halfway between x and y? You would have to formulate a directional derivative to figure out how quickly the function is changing in that direction. So your v, if I want the point, if I want the direction halfway between x and y, I could use this as the direction for my directional derivative. It's halfway between the x and y positive directions. Okay. Anyways, moving on. This says the gradient vector points in the direction of the greatest rate of increase. So I could ask you on a test, here's a function. At a given point, what's the direction this function is increasing the fastest? And all you'd have to do is find the gradient, but it's just a tricky way of describing what the gradient is. The gradient is the direction that your function is increasing the fastest. And that means the negative gradient vector is going to point in the direction of most rapid decrease. So it's the least rate of increase, or it's the most negative rate of increase, if you want to think about that. And so let's talk about what a proof would look like for this statement. How do I prove that the gradient vector is going to point in the direction of the greatest rate of increase? So the greatest rate of increase is going to be the maximum value of the directional derivative. So choose v to be any direction you want, right? But if you choose the right value of v, we'll get the maximum directional derivative. And then let's write down the directional derivative formula really quick. And of course, that's the same thing as this. Now define theta to be the angle between the gradient of f and my direction vector v. And with this dot product formula, what do we know about the dot product? I know that the dot product between the gradient of f and that unit direction vector v is going to be the same thing as the norm of the gradient times the norm of this vector times cosine theta. Right? We learned that earlier in the semester in our first classes. So I've got the norm of the gradient times this. What is the norm of v divided by the norm of v? 1. Yeah. Times cosine theta. And now ask, what value of theta maximizes the directional derivative? What's the maximum value of cosine? Cosine tops out at 1. And what value of theta do I need? 0. Because cosine of 0 is 1, and every other value of theta is going to give me a number less than 1. 2 pi doesn't count. So the answer is theta equals 0. Theta equals 0. You know, theta is the angle between the gradient and the direction we choose. So if the angle between them is 0, we're talking about the direction of the gradient. That's the proof. Okay? Now the second part of this little theorem says that the negative gradient vector points in the direction of most rapid decrease. In other words, whenever I get the idea that I want to get the most rapid decrease of my function f, that means I want to minimize the directional derivative. We want to find the greatest negative value of this directional derivative, which means I want to minimize the directional derivative. And if I do that, I would ask, what value of theta minimizes this directional derivative? Pi, yeah. If theta is equal to pi, cosine of pi is -1. And that would give me the least value of this directional derivative. And if theta is the angle between the gradient and the direction vector, pi is 180 degrees. Pi is saying turn around and look in exactly the opposite direction. And that's the direction of most rapid decrease of your function. Okay, so finding the gradient means we find the direction that our function is increasing the most rapidly, and if I take the negative of the gradient, I'm pointing in the opposite direction, that's the direction our function is decreasing the most rapidly. So that's good to know. A level set, I think we've talked about this before, but a level set of a function refers to the set of all input values that result in the same given output value. Okay? If you've got a function of two variables, you can represent that as a surface in space. And the level set of a surface would be a level curve, right? It's like a horizontal slice through the surface would end up giving you a curve that intersects there. Let me show you an example. We'll try GeoGebra. Let's try 0.5 x squared minus 0.25 y squared. See if that does anything. Okay, so I get this nice surface where z is a function of x and y. And in GeoGebra, if you want to try this at home, you should try this at home. If I want the level set where z is equal to 2.5, I'm going to type in z equals 2.5. So you can see where this plane is slicing through my surface. And to get the level curve, you would look at the intersection between the blue plane and the purple surface. And that intersection is a curve. GeoGebra does have a tool. If you click on Tools and click Intersect Two Surfaces, then you've got to select the two surfaces you want to intersect. And we'll see if it did anything. Yeah. So now you can see in black, that's the level curve. In other words, that's the level set. That's the set of all x and y values that give me exactly the same z value for my function. Okay? If I have a function of three variables, then I represent that geometrically as like a scalar field that assigns a scalar value to every point in space. And in this case, a level set is called a level surface. So we'll take a look at exercise 5 here that says, consider the function x squared plus 2y squared minus 3z squared. And we're going to graph its level set where the function is equal to 1.5 in GeoGebra. And the way to do this in GeoGebra, I think, is just going to be type in x squared plus 2y squared minus 3z squared equals 1.5. And this should give us an implicitly defined surface. That would be the level surface. Let's give this a try. So that's it. Every point on the surface is going to give me the same value of that function g. So the values of the scalar field are exactly the same on every point in the surface. Okay? Questions so far? Nope. So the reason we talk about level sets and gradient in the same lecture is because the gradient is going to be orthogonal to the level sets. You might have a crazy level set that looks like this, and you wonder, what's the gradient at this point? Well, it's always going to be pointing in a direction orthogonal to the level set. Imagine those are little gradient vectors along my level set. So why is the gradient orthogonal to level sets? Because if at some point P, we'll call this point P, I choose a direction that's keeping me inside the level set. Let's make that my direction vector V. What is the directional derivative of my function in the direction of V? 0. Why is it 0? Because the output of my function stays constant when I remain inside the level set. So if I'm moving in a direction inside my level set, the function doesn't change. The derivative is 0 because the derivative tells me how quickly is my function changing. So the directional derivative in a direction inside my level set is 0. Also remember that this directional derivative is the dot product between the gradient and the direction. And we're assuming that the gradient is not 0. The gradient is the direction, it is pointing in the direction of the steepest increase. And so if your gradient is 0, the function has to be just a flat constant function with no change anywhere. Does that make sense? Because if 0 is your greatest rate of increase, then it's 0 all over. So we're assuming the gradient is not 0. We're assuming this function is not a constant function. So the gradient's not a 0 vector. Also, this vector v is not a 0 vector. It's pointing in some direction. And so the only way that the gradient of f dot product with the gradient of v can give me a 0 is if the gradient is orthogonal to the direction we chose. So that's the proof. And again, this is interesting because that means if I were to zoom in really close to any part of any function, I could draw some kind of diagram like this, where here's my level set, and there will be some direction of steepest increase given by the gradient. There will be some direction of steepest decrease given by the negative gradient, and the level set is orthogonal to the gradient, and the level set is orthogonal to the negative gradient. So those are all at like 90-degree angles with one another. Okay, find a vector orthogonal to the surface at the point 1, 1, 1. This is a surface because I'm defining my coordinate z as a function of coordinates x and y in space. So I'll show you how to do this. First, rewrite this as a level surface of a 3-variable function. What I mean by that is, if I were to define the 3-variable function x squared y plus natural log of x over y minus z, then this is a level surface where the function is equal to 0. All I had to do was subtract z from both sides. And this is a level surface where the function is equal to 0. And since the gradient is orthogonal to level sets, I just have to find the gradient of this function f that I just invented. So the gradient of f is going to be the partial derivative with respect to x, which is going to be 2xy. The derivative of natural log is 1 over x. And then the partial derivative with respect to y would be x squared. And then the derivative of 1 over y would be negative 1 over y squared. And then the partial derivative of f with respect to z would be negative 1. So this gradient vector is going to be orthogonal to the surface. And then if I want the point 1, 1, 1, I just have to plug in x and y and z are 1. And I get 2 times 1 times 1 plus 1 over 1. 1 squared minus natural log of 1. And then there we go. That's my answer. All right, does that strategy make sense? You get an explicitly defined surface, but then you rewrite it as a level surface of some multivariable function. You remember the gradient is orthogonal to level sets, so the gradient will be orthogonal to my level surface. Then you find the gradient. That's your answer. All right, one more question. Find a plane that's tangent to the surface at the point 1, 1, 1. And it's the same as before, right? So I already remember that at the point 1, 1, 1, well, I already forgot. 3, 1, negative 1. I thought I could remember. So this is true. At the point 1, 1, 1, this was my gradient vector. How do I find a plane if I have a vector orthogonal to the plane? In other words, how do I find the plane if I already know the normal vector? You gotta dig way back in your memory. Yeah, my standard form for a plane equation said something like this. A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. I think that was it. What do I choose for A? 3. Because A, B, and C were the entries of my normal vector. What do I choose for x0? 1. Because x0, y0, z0 were just the coordinates of any point on the plane. And so you can clean this up and make it look like the general form. I've got a -3, a -1, and a +1, so it's going to be -3, or I could do that. I think that might be what we say for general form. Equation for a plane. So ideally, this plane should be tangent to the surface. Let's see if this plane is tangent to the surface. This is how I check my work. We're going to say z is equal to x squared y plus natural log of x over y. Z is equal to x squared y plus natural log of x over y. And then we're going to type in my plane equation, 3x plus y minus z equals 3. And I'm hoping that at the point 1, 1, 1, we see that this plane intersects the surface and has all the same directional derivatives as the surface at that point. And maybe it's a little bit hard to see, but I think that's true. That little hovery point that says A is the point 1, 1, 1. And this blue plane is slicing through that purple surface, intersecting it at that point. And at the point, the plane and the surface have all exactly the same directional derivatives in every direction. That's what makes it a tangent plane. Okay, any questions about that? So if you got that question, you would first rearrange it to look like a level set, then find the gradient of that function, so you get a normal vector to the level set, and then you would use that normal vector to write the plane equation, because you can always write a plane given its normal vector, and a point in space belonging to the plane, and that's given to us here, so you can make it happen for any surface now. How do you feel about that, Blake? Do you have positive emotions about that? Are you mad? Are you upset? Disappointed? Yeah.
I just get confused sometimes like which one you want your A. Now it's here.
Yeah. What about the rest of you guys? Tell me how this makes you feel.
How it makes you feel.
Huh?
How it makes you feel.
Tangent planes?
I didn't even process what happened. Now I'm sick. I went like this yesterday and I was like, yeah, this is vertical. And I was just done.
That's when you knew. Do you want to work? I mean, how many minutes do we have left in class? 25 minutes? Do you want to work some questions from the homework page today? Is there anything that sticks out at you? Anything you want to go over?
Maybe exercise 7.
Okay.
The last problem.
Let me pull it up. So you're going to do the last problem on exercise 7 that says z equals natural log of blah, blah, blah. Okay. Let's do it. We have z equals the natural log of x squared plus y squared. And the point that we're given is 3, 4 natural log 5. Yep. So, what am I trying to find? A vector orthogonal to the surface. Okay, we're just trying to find a vector orthogonal to the surface. What I would do is think 0 equals natural log of x squared plus y squared minus z. So this could be the level set of a function. And I know that the gradient of this function is going to be orthogonal to the level set. So this is exactly what I want, a vector orthogonal to the surface. And to get the gradient, I first have to take the partial derivative with respect to x. And the derivative chain rule says first take the derivative of the outside function, which is 1 over x squared plus y squared. Then multiply times the derivative of the inside function, and the partial derivative with respect to x of the inside function there would be 2x. And then I don't have to work that hard to figure out the same thing for y, because this equation is symmetric with respect to x and y. And then for z, the partial derivative of f with respect to z is just -1. So here is the formula to give me my gradient at any point x and y in space. That will give me the gradient of my function, any point x, y, z. But it turns out it's not even dependent on z. And then specifically to get a vector at this point, I've just got to plug in x equals 3, y equals 4, z equals natural log of 5. And so the vector would be, let's see, 2 times 3 divided by 25. And then 2 times 4 divided by 25, -1.